Hey everyone, welcome back. Today, we're going to be taking a deep dive into the world of sparse autoencoders,
Okay.
or SAEs, as I'm sure you've heard them called before.
Mm.
And we're going to be looking at how they're being used to unlock some of the mysteries behind language models.
Yeah, it's like we're trying to break the secret code of how these models understand and generate text.
Exactly. But, the thing is, even with these powerful tools, there are still some puzzles to solve, some dark matter we need to explore.
Absolutely, and that's what makes it so fascinating.
Yeah, for sure. And that's exactly what we're going to be looking at today.
Right, we'll be diving into a paper that explores this dark matter, the errors that SAEs make when they're trying to reconstruct the activations of a language model.
Oh, wow. Okay.
And what's so intriguing is that these errors, they aren't just random noise.
Okay.
They seem to hold valuable clues about how these models actually work.
Oh, that's awesome. I'm already hooked. But before we get too deep into the mystery, can you just give us a quick rundown of what sparse autoencoders are and how they work?
Yeah, of course. So imagine you have a complex image, like a painting of a landscape.
Okay.
And you want to break it down into its most basic components.
Right.
Like the building blocks of color and shape.
Yeah.
Sparse autoencoders, they do something similar, but with language model activations.
Okay.
They learn a set of essential features, almost like a dictionary.
Yeah. Okay.
That can be combined to reconstruct the original activation.
So it's kind of like figuring out the secret recipe for a dish.
Yeah.
Figuring out all the ingredients and spices that create its unique flavor.
Yeah, that's a great analogy. And the sparsity part,
Right.
that means that only a small number of these features are active at any given time.
Okay.
So it's about finding the most essential ingredients, not just throwing everything in the pot.
Gotcha. Yeah.
This helps make sure that the features are truly independent and meaningful, not just random elements.
Okay, so it's like finding those core elements that capture the essence of the whole thing.
Exactly.
But you mentioned earlier that even these clever SAEs, they still make errors.
Right.
And that's where the real mystery begins, right?
Yes, exactly. And the really surprising thing is that a good chunk of these errors are actually predictable.
Whoa, predictable.
Yeah. So the researchers, they found that just by looking at the original activation vector, they could often predict how big the error the SAE would make was going to be.
Wait, hold on. That's pretty wild. If the errors are predictable, wouldn't that mean that there's some sort of structure to them? Like something we could understand and learn from?
That's one of the key insights from this paper.
Oh, wow.
The researchers suggest that this predictable error, it's largely due to something called linear error, which basically represents features that the SAE just hasn't learned yet.
Okay, so it's not that the information isn't there in the activation. Right. It's just that the SAE doesn't have the right tools to capture it yet.
Yeah. If you have a limited vocabulary and you're trying to describe a complex concept, you might miss some details because you just don't have the right words.
I totally get that, yeah.
And this is where it gets even more interesting, because the paper introduces this new type of error they call introduced error.
Introduced error. Okay, I'm intrigued now.
So this refers to errors that are not actually inherent to the activations themselves.
Right.
But they stem from limitations in the SAE architecture itself.
Okay, so what does that mean? Is it like a glitch in the system?
Not really a glitch, but more like a consequence of how the SAE is designed.
Okay.
Imagine you're building a model of a skyscraper, but you can only use Lego bricks.
Yeah, okay.
You might not be able to capture every single detail of the building simply because of the limitations of Legos.
Yeah, because of how Legos work, yeah.
Exactly.
That makes sense.
And that's kind of similar to what's happening here with the SAEs.
So even with all the best intentions and a huge vocabulary of features, the SAE might still introduce some distortions.
Right.
Just because of how it's built.
Exactly. And this adds a whole new layer of complexity to understanding these errors.
Wow.
The researchers, they even found that some errors are not linearly predictable at all.
Oh, wow.
Suggesting that they might be coming from this introduced error component.
So it's like trying to fit a square peg into a round hole.
Yeah.
Even if you had all the right pieces, it just wouldn't work.
Right.
That definitely points to something deeper going on.
Right. And the researchers, they went through a lot of effort to understand these different types of errors.
Okay.
They designed some really clever experiments to probe their nature and figure out what they're made of.
So they were like detectives trying to gather evidence and understand these errors.
Exactly. And one of their key tools was this thing called the norm prediction test, which helped them distinguish between the linear and nonlinear error components.
Okay. I think you're going to have to explain that one a little bit more.
Sure. So the norm of a vector, in this case the error vector, refers to its length or magnitude.
Okay.
You can think of it like the distance between 2 points.
Okay.
The researchers found that if the errors were mainly due to missing features, that linear error component,
Right.
then their norms could be predicted fairly accurately just from the original activations.
So are they saying that if the SAE is just missing some information,
Yeah.
we can predict how much it will mess up based on how complex the original information was?
Exactly. Like, if you know the general size and shape of a puzzle piece, you can guess how much space it will take up, even if you haven't found the exact piece yet.
I like that. That makes a lot of sense.
Yeah, and so what about the errors that can't be easily predicted?
Yeah.
The ones that don't really fit into that linear error category.
Right, exactly.
Well, they applied this norm prediction test to those as well.
Okay.
And the nonlinear error components scored much lower on this test.
Interesting.
Suggesting that it's made up of something more complex.
Right, something beyond just missing information.
Exactly. Potentially something related to that introduced error we talked about.
So it's like finding a puzzle piece that doesn't belong to any puzzle.
Yeah.
Its shape is unique, and it doesn't match any existing patterns.
Right.
Okay, now to really understand this, they did something pretty clever.
Yeah.
They tried to train new SAEs specifically on these different types of errors.
Right.
Hold on, they trained an SAE on the errors of another SAE. I'm not sure I follow.
Yeah, so it's a brilliant way to see what those errors are really made of.
Okay.
So if the linear error is truly because of missing features,
Right.
then an SAE trained on that error should be able to learn those features.
Gotcha.
And makes much fewer errors, right?
Oh, okay. So it's like a test to see if those missing pieces were really there all along.
Exactly.
And did it work?
It did. The SAE trained on the linear error was able to get a much lower reconstruction error.
Wow.
But the SAE trained on the nonlinear error,
Yeah.
it didn't improve as much.
So those missing pieces were
Yeah.
definitely there in the linear error.
Yeah.
But the nonlinear error, that seems to be a much tougher puzzle to solve.
Right. It might be hiding some deeper secrets about the SAE itself.
This is fascinating. But wait, to understand what these new SAEs were learning, they used this technique called automated interpretability.
Right.
They used another language model to explain what each feature learned by the SAE was actually doing.
Yeah, essentially they were using one AI to explain the thoughts of another AI.
That's pretty meta.
It is.
And what did they find?
So the features learned from the linear error were much more interpretable.
Okay.
Meaning they could be more easily translated into concepts that we as humans can understand.
So that further supports the idea that the linear error is mostly from patterns that can be learned, while the nonlinear error might be something more complex, something we don't fully grasp yet.
Exactly.
Okay, my mind is officially blown. We've gone from trying to understand these SAEs to almost like performing a psychological evaluation on them.
It's true.
But before we get too lost in the weeds here, I'm really curious to hear more about those experiments you mentioned earlier.
Yeah.
The ones where they really dug deep into these different types of errors.
Right.
Can we talk about those a bit more?
Absolutely. Well, we'll explore how they separated the linear error from the introduced error,
Right.
and how they pushed the limits of what these SAEs can really learn, revealing even more about these language models.
I'm excited to hear more.
Welcome back. Last time we were talking about how researchers are using those sparse autoencoders, those SAEs, to really dig into the workings of language models.
Yeah, and it felt like we were in a detective novel.
Yeah.
Trying to decode all these hidden messages behind these errors.
Right, exactly.
And you left us on quite a cliffhanger. Talking about these fascinating experiments the researchers used to probe these errors even further.
Right, yeah. So one of the coolest experiments they did was looking at how the errors made by SAEs changed as they made them bigger.
Okay.
So you'd think that, like, intuitively a bigger SAE with more features would just make fewer errors overall, right?
Right, yeah.
It turns out it's not that simple.
Okay, so it's not just a matter of brute force, like throwing more features at the problem.
Exactly.
Okay, so what's going on then?
Well, remember we talked about those two main types of errors?
Yeah.
Linear and nonlinear.
Yeah, I remember.
They actually behave quite differently when you make the SAE bigger.
Okay, so the linear error, those missing words, should decrease as you add more features, right?
Right.
But that nonlinear error, the one that might be due to the inherent limitations of the SAE,
right,
that might be a tougher nut to crack.
exactly. And what they found is that how the error changes for each individual word as you increase the SAE size is actually quite predictable.
Hold on, are you saying they can predict how the error will change for each specific word, even before they train the larger SAE?
Yeah, pretty cool.
How is that even possible?
Well, it all goes back to that introduced error concept.
Okay.
Because this type of error is mostly driven by limitations in the SAE itself.
Right.
It stays relatively constant even as you add more features.
So it's like the SAE is leaving its own mark on each word, a kind of error fingerprint.
Yeah, a signature.
That's determined by its design, not the actual information in the activation.
That's a great way to put it.
So it's like recognizing an artist's style, even if they're painting something completely different.
Exactly.
Okay, that makes sense. But why is this finding so important?
Well, for a couple of reasons.
Okay.
Firstly, it really shows how important it is to understand and maybe even fix that nonlinear error.
Yeah, if we want SAEs to show us the full picture of what's going on in these language models,
right,
we need to find ways to reduce that dark matter as much as possible.
Yeah, it's not just about building bigger SAEs.
Yeah.
It's about building smarter ones.
Ones that don't have as many limitations.
Right.
So we can really understand the underlying features.
That's the goal.
Okay. And you said there was another reason this finding is important.
Yeah, this per token scaling behavior also has practical implications.
Like what?
Imagine you're trying to analyze a really tricky activation.
Okay.
By understanding how the error scales, you can estimate how much of that error is due to missing features, which could potentially be solved by a larger SAE versus how much is due to those SAE limitations that we talked about.
So it's a tool for figuring out the strengths and weaknesses of our SAEs.
Exactly.
Okay, that's really useful. Now, remember how we talked about those more powerful encoding algorithms like gradient pursuit?
Yeah.
I was wondering if they tried using those to reduce the nonlinear error.
That's a great question, and they did.
Okay, and?
They found some pretty interesting results. And they found that while using gradient pursuit did lead to a reduction in the overall reconstruction error.
Okay, so that's good news, right?
It is. It means the reconstructions are getting more accurate.
Right.
However, it didn't really change the nonlinear error component that much.
So even with this fancier encoder, the nonlinear error was still hanging around.
Yeah, it seems like they hit a wall.
Like a fundamental limit.
Exactly. And it suggests that maybe the nonlinear error can't just be fixed by tweaking the encoding process.
Okay, so if more powerful encoders aren't the solution, then what is? Are we stuck with this nonlinear error forever?
Well, the researchers didn't give up that easily. They had another idea.
Okay, tell me more.
They thought, what if we use information from nearby SAE layers to try and predict and maybe even reduce the nonlinear error?
Ah, so instead of looking at each layer in isolation, they started considering the context of the surrounding layers.
Exactly. And guess what?
Did it work?
It actually did. Yeah. By using information from earlier SAE layers, they were able to reduce that nonlinear error.
Wow. So it seems like each layer provides a different piece of the puzzle.
Yeah, a different perspective.
And by putting them all together, we get a clearer picture.
Yeah, exactly.
This is all so fascinating. But before we wrap up this part of our discussion, I want to go back to something you mentioned earlier. Predicting the direction of the error vector.
Right.
We didn't really get into what that means.
Yeah, you're right. So remember how we talked about the norm of the error?
Yeah, like measuring how big the error is.
Right, exactly. Well, the error is actually a vector.
Okay.
Which means it has both a magnitude or size and a direction.
Okay, so it's not just about how far off the SAE is, but also which way it's off.
Exactly.
I'm having a little trouble picturing what that means, though.
Okay, well, think of it like a compass.
Okay.
Predicting the norm of the error is like saying how far the compass needle is pointing.
Okay.
While predicting the direction is like saying which way it's pointing. Ah, okay. So they were trying to predict not just how big the error was, but also where it was pointing.
Exactly.
That's pretty ambitious.
It is, and they found that predicting the direction of the error vector was possible to a certain extent.
Okay.
Especially for those smaller SAEs. But as the SAEs got bigger, their ability to predict the direction decreased.
Interesting. So it's like the larger SAEs are dealing with errors that are more chaotic and unpredictable.
It seems that way.
This just keeps getting more and more complex.
That's what makes it so exciting. each answer leads to more questions.
Right. And speaking of pushing the boundaries even further,
Yeah.
we haven't even talked about those experiments where they trained SAEs directly on different types of errors.
Right. We can explore that next.
It sounds like a whole new level of mind-bending analysis.
It is. We'll dive into those experiments and see what else we can learn about these SAEs and language models.
All right, so we're back and ready to finish our exploration of these sparse autoencoders and all those fascinating errors.
Last time, you were talking about how the researchers used information from nearby layers to try and predict and reduce that nonlinear error.
Yeah, like using the context to get a better understanding.
Exactly.
Yeah.
But you also mentioned that they went a step further and actually tried training SAEs directly on different types of errors.
Right.
Now, that sounds like a really wild idea.
It is pretty clever, though. Remember we talked about how linear error probably comes from those missing features? Those words the SAE hasn't learned yet.
Yeah, I remember.
Well, they tested that idea in a very direct way.
Okay, I'm curious, how do you even train an SAE on an error?
It does sound a little counterintuitive.
Yeah.
But think about it this way. They took the errors from one SAE, specifically the ones they thought were linear errors,
Right.
and used those errors as the input to train a brand new SAE.
Oh, okay. So they're basically saying, hey, new SAE, here's a bunch of mistakes that probably mean there are some missing features. See if you can learn from them and do better.
Exactly.
And what happened?
Well, they found that the new SAE that was trained on those linear errors,
Right.
it actually had a much lower reconstruction error than the SAE trained on the nonlinear error.
Wow. Okay, so it really was like giving a student a list of words they missed on a spelling test.
Yeah, exactly.
They're able to learn those missing pieces and improve.
Right.
So that's pretty convincing proof that linear error does indeed contain valuable information about those features.
Absolutely. And remember that automated interpretability technique we talked about?
Yeah, where they use another language model to explain what each SAE feature is doing.
Right. Well, they use that technique again to analyze the features learned by these new SAEs.
Okay, so what do they find? Were the features learned from the linear error more understandable?
Yes, definitely. The features learned from the linear error were way more interpretable.
Okay.
Meaning they could be translated into things we can understand much more easily.
Right.
And that makes sense. If those linear errors are mostly made up of missing features, then those features should be more recognizable once they're learned.
Right. It's like the SAE trained on linear error was able to fill in the gaps in its understanding, creating a clearer picture of those activations.
Exactly.
Now, this brings up an interesting point, though. If we can train SAEs to learn from these linear errors, couldn't we use this knowledge to build better SAEs right from the start?
You're exactly right.
Instead of seeing errors as just something bad,
Yeah.
we could use them as a guide to make the SAEs more sensitive to those missing features from the very beginning.
Exactly. This research is really exciting because it gives us a whole new way of thinking about SAE design.
Yeah, it's not just about building bigger SAEs.
Right.
It's about building smarter SAEs.
Exactly.
That can really capture the essence of these activations.
Absolutely.
This has been an incredible journey into the world of sparse autoencoders.
It has.
We've really gone deep exploring their strengths and weaknesses and their potential.
We've learned a lot.
And along the way, we've gained some valuable insights into these language models themselves.
Right. They're more complex than we might think.
Yeah, and the tools we use to understand them, like these SAEs, can both help us understand them better and sometimes make things more confusing.
Yeah, it's a constant back and forth.
This research really highlights that we need to keep questioning our methods and keep pushing the boundaries of what we know.
And embracing the mystery of what we don't know.
Exactly. And to our listeners, if you want to learn more about all these fascinating details,
Yeah, please do.
be sure to check out the original research paper. You'll find even more in-depth information there.
There's always more to learn.
Absolutely. So keep exploring, keep learning, and keep those minds engaged.